Hello. How's it going? How's everyone enjoying Cascadia so far? Awesome. I've been loving it myself. It's my first time here, and the talks and the people and everything has been amazing. But you know one thing I really don't love, Cascadia? It's being pinged on that bug that I am very sure I solved already a few times now. This is like the third time this bug has popped up. And each time I thought we'd fixed it finally. So it's getting a little old. But let's start from the beginning. So we're making a to-do list app. And we decided to use React Query for loading data from the server. At first, this use-to-do hook here was a pretty simple wrapper around React Query, and it was working really well. But then someone decided to add a format option to that hook and to process the to-dos. And after a while, we started seeing a lot of slowdown on low-powered devices as more and more code was using that option. And don't ask me why formatting to-dos is so expensive. This is what we might call a contrived example. Now, the first fix we merged was to simply add use memo here, so we wouldn't be constantly rerunning the format function. But that did not fully resolve it. It turned out it wasn't just re-renders that were the issue. The initial render was also very expensive because every time we called use to-dos during that pass, it would still call format. And it turned out we were doing that a lot. So on to round two. We ended up making a hook specifically for defining and memoizing these format functions. Here we pass in a key, and much like the one you pass the use query, it memoizes that and it gives you back the specific function instance. So this finally fixed the issue, and now we're guaranteed to only call the format function once for each unique callback. As long as everyone's using the hook, we should be good. I think I might have an idea of what's going on here. Let me just do a quick search across the code base, and yep, there it is. Somebody forgot to use the hook, and we ended up with the same problem as before. All right, fixed. Now, like I said before, this example is a bit contrived. But it is similar to situations I've actually seen when I've been digging around and debugging hooks in large and complex code bases. There's all of these little nuances that you constantly have to keep an eye out for, and if you aren't using them just right, it ends up feeling a bit like this. And I'm not the only one. In fact, Cloudflare just had an outage because of a use effect bug. I call this uniquely frustrating experience reactivity hell. Now, you might recognize that as a callback to, well, callback hell. And if you recall, we escaped callback hell not by coding around it, but by introducing a new primitive, the promise. Promises made confusing async code much clearer and easier to follow. And eventually, async await came along and made it even better. Now, I believe we can do something similar when it comes to reactivity. This has been my passion project for the last 8 years, on and off. And along with a lot of really talented devs across the JavaScript ecosystem, I think we've collectively developed a new primitive that can help us resolve this situation once and for all. So today, we're going to be escaping reactivity hell. But to do that, first we're going to need to look back to the past to learn what worked last time we escaped hell. That's right, folks. We're going to return to callback hell. Yes, I too thought we'd escape forever, but if we're going to get out of this, we need to learn a few lessons from last time. So let's talk about callbacks. No, not those callbacks. I want to go back to C. Now, the reason I want to bring us back to C is because C is very close to the metal, and it's a great place for us to think about what exactly a callback is in the first place. In the most basic sense, a callback is a pointer to a location in program memory. When we're passing a callback to another function, we're essentially saying, hey, I want you to call this other function later. Here's where it is in memory. And then the function we're passing it to does its thing, and at some point later, it jumps to that location. But the thing is, that's often not enough information. We might have many callbacks running at the same time and using the same code. So we need to be able to tell them apart. So we have to deal with passing context, which is this variable here. The context can be anything, a struct, a string, a number. The important thing is that it allows us to differentiate between different instances of a callback if we schedule it multiple times. Now you can imagine how messy these old school callbacks get if you start to chain them together, managing different contexts and their memory and so on and so forth. So let's move on to the next iteration, closures. Okay, nice, we're back in TypeScript land. Big breath out, we're safe now. The garbage collector's back. So closures allow us to do that song and dance of capturing and referencing context in line, directly in the function where we schedule the callback. We're not jumping from one function definition to another. We just define our closure, and it automatically captures the current scope of the context. Under the hood, though, this is pretty much the same as before. Closures have both the pointer to the function itself in program memory and the pointer to the context, the current scope. But the complexity of capturing and managing that context is all handled by the closure, and that means we can instead focus on making our code better and nicer and clean and readable and just nice. All right, there was a reason we called it Callback Hell. Okay, so now we get to promises. Much better. Now, promises improve things by allowing us to chain all these async actions together so we could see the flow as a series of steps. Again, under the hood, they're doing essentially the same thing. Promises contain callbacks, which they call when they resolve or reject. So fundamentally, they're just abstracting and standardizing how we call the callback. Now, one interesting thing about this abstraction is that it actually narrows the scope of what's possible as well. With a normal callback, there really isn't any guarantee that it's only called once. In fact, that might be what you want in many cases. You want it to be called many times, like with event listeners. But promise callbacks are only called at most once when the promise settles. And this is because promises only handle symmetric async, one request, one response. This is going to be important in the next step, which is when we see the real magic, async await. So with async await, we now have a function that looks like a normal function with a couple of extra keywords. And once again, under the hood, it's all based on promises, which means we're doing essentially the same thing we've been doing. We're capturing context, pausing execution, and then restoring that execution later with that context. Now, this is where I think we start to see some of the major benefits of promises outside of just flattening the callback tree. We're ultimately hiding all these details of async behind a few keywords. So we don't have to even think about them, at least locally. And we can just focus on writing standard functional code. The reason we're able to do that is because promises narrowed the scope to just sequential steps. Async await would not make sense if it was based on callbacks, because if you called the callback more often than once, you could have it running multiple times, out of order. It wouldn't make sense. It would be impossible to reason about. Together, these improvements fundamentally simplify our code and make it easier to maintain and understand. We went from having to manually manage multiple pointers in memory for every async action to a tidy, self-contained syntax that handles it all for us. Okay, so let's get back to reactivity. What have we learned from Callback Hell? And how can that help us in our struggles with reactivity? First off, we learned that we should narrow the scope. Promises decided to only handle symmetric async, one request, one response. That is the core of what enabled async await syntax, which is what allowed us to start thinking about async as just plain functions again. So we should look for some way to narrow the reactive problem space. The second thing we learned is that we likely want to introduce a monad to help us do this. Dropping some computer science lingo here, promises are actually monads, or close, don't at me type people. Monads are about capturing context and then sequencing computation with that context. And that's exactly what we saw with promises under the hood. They capture the next step in the program, all the variables we need to execute that next step so that we can do that later. So what we want to do that, but for reactive updates instead. And the third thing we learned is that ideally we want our solution to layer naturally on top of the fundamentals of JavaScript that we already know. We don't want to completely rewrite our apps just to add reactivity. we want to be able to add it progressively to our functions in a way that can interop with standard code easily. OK, so what does this solution look like? To start, I think we can take some cues from what React, Elm, and others did by pushing us toward a more functional model in the last decade. One thing that they really got right is that it's much easier to focus on incrementally updating the results of functions than on the state of objects. So when we call a function, we can think of that as a tree of computation, where each node in the tree is another function going deeper and deeper into the graph. It's useful to think about functions in this way because it shows us the relationship between them more clearly. For instance, take function memoization. That's essentially us saying that we know that this subgraph is identical to this other subgraph we saw previously, and we can essentially just reference the same node again. Now, what's interesting is that this appears to work in reverse as well. Let's say that we know that the value of this node deep down in the tree has changed, and we want to know if that means the root node has also changed. What we don't know yet is if any of the nodes in between have changed. But because the nodes are functions, we can find out by simply rerunning them. If the results are different, that means that we need to rerun the parent node. And if they're not, we don't. So with async, we wanted to resume the function at the very next step, after the task had finished. So promises captured all the context we needed to do that. With reactivity, we want to resume the function from its children first, whenever they may have changed. So for our design, all we need is a monad-like data structure that captures all of the context needed for us to know if a function's children could have changed. What is this data structure, you ask? Well, if you read the description of my talk, then it probably comes as no surprise that it is, in fact, signals. And they even have a very early, signals are an emerging reactivity primitive that has been adopted by many major frameworks and libraries. And they even have a very early proposal in the TC39 process. Now, if you're a nerd like me, maybe you've already read the spec and played around with them a bit. But if not, I'm going to give you a quick primer. We'll use Preact Signals API here because it's a pretty popular framework. And I may have used it as inspiration for something that's coming up in the next few slides. So here we have a basic example of how to define both state and computed signals with Preact. Pretty much every flavor of signals out there has these two core types of signals. You have where state signals represent root state in your application, and computed signals represent derived state. In this example, we're creating two state signals, one for first name and one for last name, and then we create the full name computed that references both of them. Now, the first time we access fullname.value, it'll run the computation function and access first name and last name. And it also tracks that it used those values. The result of that function is then cached, and full name will continue to return the cache value until the track dependencies change. Computeds can, of course, also track other computeds as well, and they'll change when those change. So you can see how this is exactly the data structure we were looking for. When state changes, computeds rerun from the bottom up lazily. But there is a bit of a rub. Computeds aren't functions, which means we can't just drop them in as replacements in functional code. We instead have to create and manage each computed instance separately, which is a bit of a pain. What if we didn't have to do that? What if we could instead define functions that automatically handled all of those details for us, kind of like how you can memoize a function? I'd like to introduce y'all to Signalium. Signalium is a signal library that explores what it looks like when we start to layer in signals at the language level, like we did with promises and async await. And in Signalium, we can define reactive functions. Now, at first glance, reactive functions may look just like computeds. But the difference is that you can pass parameters to them just like normal functions. And they memoize based on both their parameters and the signals they use. So they'll only rerun if one or the other changes. You can see this memoization live in this example here, which is showing an actual trace. It shows how the functions rerun incrementally and stop propagating if the results haven't changed. All of this is also done lazily. We only do this when one of the parent functions has been called or used. And because this is all lazy, you can actually use conditional logic in reactive functions. There are no rules of signals in the same way that there are rules of hooks. So that covers normal functions. Now what about async? Well, with Signalium, you can also define reactive async functions. And they'll return promises just like any other async function. You can also await these promises inside other reactive functions, just like you would normally. And it'll all update reactively, just like you would expect when promises resolve. But the real magic is that these promises are also reactive. Here, you can see that the promise exposes these isPending and value properties. And we can use those to return either the resolve value or default value if we haven't resolved yet. And that output will update whenever the promise completes or changes states. This effectively allows us to escape the function coloring problem that plagues async code. If you can react to async state over time, you can turn async state into synchronous output. And just like standard reactive functions, async functions also update from their children. So when we await multiple children together, the parent will wait for all of them to finish before propagating. Meaning you don't have to worry about partial updates or in-between states or wrapping your async in a transition. You can just use promise.all and await everything like you would normally. So that's that for async. Or is it? Remember earlier when I mentioned that promises only solved symmetric async, one request, one response? Well, that's the lion's share of async. It's definitely what we do the most in our apps. It turns out that some problems can really only be solved with asymmetric async. Things like subscriptions, polling, background thread communication, et cetera, et cetera. And once again, to React's credit, this is something they figured out a long time ago with hooks. In fact, managing a subscription is the basic example for useEffect in the React docs. Now, useEffect can do a lot of weird, wacky, and dangerous things, but it's extremely useful for creating these sorts of effect as data source types of constructs. And the reason why is that these types of things all must be torn down when they're no longer in use. If you subscribe to something and then leave that subscription open forever, eventually you're going to have more and more of them, and that's going to overload your app. useEffect gives us a way to do that, and it gives us a way to do it deeply within our function graph. You can make a custom hook that's n layers away from your component, and that hook can set up and tear down the subscription as needed. You don't have to drill the lifecycle down from the component to that effect. Signalium has a solution for this built in, and they're called relays. Named after real-life signal relays, which are a form of repeater, Signalium relays are essentially a managed effect with state. The idea is that they relay information in and out of the graph, mediating between the graph and the outside world. Similar to effects, relays have an activate function that's called whenever it connects to the graph, and they can return a deactivate function that's called on disconnect. These functions receive write access to the relay's internal state, but the state is read-only externally. So that keeps it safe from people randomly mutating it. Now, from the perspective of the rest of the graph, the relay is just like any other node. It's just a piece of state, and it happens to update every so often due to something in the background. We can use it just like any other signal, and everything just works. So that rounds out the core main features of Signalium. To review, Signalium is a more efficient alternative to hooks. that has first-class support for all forms of async. And that works anywhere. You can use Signalium in your front end or in your Node.js API server or anywhere that JavaScript runs. Because it's not about making reactive UIs. It's about making reactive functions in general. Now, what's the impact? Earlier I said that this has been a passion project of mine for the last 8 years. You might be wondering why. Why would this matter? Why would she spend so much time obsessing over this problem? Well, reactivity hell is something that every developer has had to struggle through at some point in their career. And that's not just because of modern web apps. It's been with us since the beginning of time. But all jokes aside, callback hell was the same until it wasn't. And while the impact of promises and async await on developer experience was pretty massive, I would actually contend that the impact on user experience was even more massive. It was just less direct. The impact was in the number of bugs that were avoided, the amount of code we didn't need to write, the spaghetti that never had time to form. My experience so far with reactive functions is they can help us do the same thing for reactivity. And you don't have to take my word for it. When we were proving this out in our wallet application, we did a proof of concept to see how much it would help to improve our performance, which was suffering from many compounding issues and a lot of tech debt. Issues that were similar to my contrived example in the beginning. What we saw in the early experimental version was a performance improvement of about 400% on initial render of one of our main flows. Better coding patterns don't just make developers' lives easier. They make apps smoother, more resilient, and better overall. Everything flows downstream, and if we're dealing with the mess in our core primitives, every line of code we add on top is going to amplify that mess. And that includes, by the way, every line of code written by AI, for what it's worth. We may be leaning more and more on our robotic counterparts to help us write code, and I'm no exception to that. But that means more than ever, we need to do the creative work to make the patterns that AI and other people replicate better, so we don't end up maintaining a bunch of unmaintainable slop. Sometimes we need to go back to the basics and rethink things from the ground up. Thanks for escaping reactivity hill with me. I think we made it. My name is Kristen. You should check out my website at xerox.com or the docs at signalium.dev. Have a great rest of your conference.